This will be on continuous functions, and so I'm going through the exercises for those, or at least most of them. Suppose you have f of x is 2x plus 7. I want to show it's continuous at every point. Well, if you look at f of x minus f of y, it's 2 times x minus y. So if you pick x and you let y be closer to x than epsilon over 2, then f of x minus f of y will be less than this 2, and this will be smaller than epsilon over 2, and that's epsilon, see? So that says that f is continuous at x because epsilon was arbitrary. Now this is the case of a function that's defined on an interval, 0 up to 1, and it also is defined at 9. So this 9 is called an isolated point. You see why it's isolated? It's way out by itself, away from this set. Okay, so I'll let f of x equal x on 0, 1, and f of 9 is going to be 5. If you like, let it be 37. It doesn't matter what it is. F will be continuous at the point 9. Now, the reason for that is that if you let delta be anything less than 8, so let's suppose delta is less than 5, then if y minus 9 is if that is less than 9, less than delta, with y element of the domain of f, well, where can y be? It can only be 9, see? Because there isn't anything closer to 9 than 5, all right, that's in the domain. And so when you look at f of y minus f of 9, it's 0. And whatever epsilon you pick, that's smaller than epsilon. So you see, it doesn't matter what value you assign to a function at an isolated point like this. The result is going to be continuous at that point. So here's another one that's more typical. F of x is x squared plus 1. And I want to show it is continuous at x equal to 3. Well, f of x minus f of 3 is this. And now suppose I let this be less than 1. Then absolute x is less than 4. And so if I have this happening, then this difference is less than 4 times absolute x minus 3. So now I'll let delta be smaller than the minimum of 1 and epsilon over 4. All right, now this minimum, that means I'm going to take whichever one is smaller. So you see, if I use this delta, then in particular x minus 3 is less than 1, and so this happens. And then since x minus 3 in absolute value is less than epsilon over 4, I have this happening. So therefore, the function is continuous at 3. Now this is a similar problem. Do it exactly the same way. So now let's let f of x equal to x squared plus 2x show it's continuous at every point. Well, f of x minus f of y is smaller than or equal to this. Now how did I get that? Well, the 2 times absolute x minus y came from this piece. The x squared part gave me this. Okay, this is where that came from. And I used the triangle inequality. Now suppose I let y minus x in absolute value be less than 1. So absolute value of y is less than 1 plus absolute x. Then if I look at this inequality, this will be smaller than this here. See, the 2 times absolute x minus y is right there. And then you have this here, plus 1. That comes from this part here, and the fact that absolute y is less than this. All right, so I get that. And so now I'll let delta be less than the minimum of 1 and epsilon over 3 plus 2 times absolute x. Then, if y minus x is less than delta, all the inequalities hold at once. And so absolute of f of x minus f of y is less than this. See, that's this up here, you see. Times epsilon over 3 plus 2 absolute x, and that's epsilon. All right, show that if you have f of x equal absolute value of 2x plus 3, then f is continuous at every point. Well, I take absolute value of the difference You see, and that's smaller than this. That's 2 times absolute x minus y. So f is obviously continuous. You could just let delta be epsilon over 3. All right, let's look at this one here. This is continuous at every value of x because if I take this one minus this one in absolute value, that's equal to this, and that's smaller than or equal to that times this. That's just factoring this difference of two squares and then using the triangle inequality, and that's smaller than or equal to 2 times absolute of x minus y. So I can just let delta equal epsilon over 2. Now what I want to do is go over a little bit why this is smaller than 2. In fact, I think I can show I can get a better estimate than 2, but I don't care. The reason why that's true is that this is less than or equal to this plus this, and that's smaller than this plus this, and that's smaller than 2. Okay, so we're done. This is continuous at every point. Now I want to point out that in this problem and this problem, the delta that I chose did not depend on the point x at where I was looking. That means that the function is uniformly continuous. More on that a little later. Now, here I want to point out that if you have any real number, there's always a sequence of rational numbers that converges to it. Now, how do we know that? Well, we showed that the rational numbers are dense. So if you take your number and you look at intervals having that number as the center, then in each of those intervals, no matter how small, you can find a rational number. And therefore there exists a sequence of rational numbers that converges to x. Now you can do the same thing with irrational numbers by showing that the irrational numbers are also dense. Now to do that, you need an example of an irrational number. Square root of 2 is such an example. Now, if I let x be less than y, there exists n so large that square root of 2 divided by 2 to the n is less than the length of that interval, see? The distance between x and y. You see? And so, if I look at all the integer multiples of this, they are spaced a distance apart that is smaller than the length of the interval joining x to y. Therefore, there has to be an integer k such that one of these is inside that interval. Now, I've just shown that numbers of this form are dense, just like the rationals. Now, each of these numbers is an irrational number because the k is rational, the 2 to the n is rational, square root of 2 is not rational. If this whole thing were equal to p divided by q, where p and q are integers, then I could multiply by this integer, the 2 to the n, and divide by this integer, the k, and I would have the square root of 2 would equal to the quotient of integers. And it's not. Okay. So that shows you these are irrational and they are dense. Now, if I look at this function, I can say right away that this function is not continuous anywhere. If I pick a rational number, I could get a sequence of points x sub n that converges to that rational number, and the x sub n are irrational. So f of x sub n would be 0, and so the limit would be 0. The value of the function would be 1. So you see it's discontinuous at all rational numbers. And similarly, it's discontinuous at every irrational number, and that includes all the numbers. Now, as an interesting incidental observation, this particular function, although it is bounded, cannot be integrated because if you look at the upper sum, say you were looking at the interval from 0 to 1. If you look at the upper sums, you'll get 1. If you look at the lower sums, you'll get 0. So there's a gap between all the uppers and lower sums. So this function has no integral. All right, here's another problem. Show there exists, suppose I look at this function. X if x is rational, 0 if x is irrational. All right. If I look at the point 0, this function will be continuous there. Because if I have a sequence of say, x sub n converges to 0, if x sub n is irrational, then the function's value at xn is 0. If x sub n is rational, the value of the function is xn, x sub n, and that converges to 0. So you see the function is continuous at 0, but it will not be continuous anywhere else. Because if you pick a rational number that is not 0, then the function's value will not be 0. And I could get a sequence of irrational points that converges to that rational point. And the function's value at all those would be 0. So you'd have the limit of 0 not equal to something non-zero. See, and so the function would fail to be continuous there. It's exactly similar if x is not 0 and irrational. All right, here's a more interesting problem. This one shows that your ability to draw pictures is totally insufficient to understand the concept of continuity. All right, so here is a function. F of x is going to be 0 if x is irrational, 1 over q if x is equal to p over q in lowest terms. Okay? So let's, what I'm going to do is I'm going to show that this function is continuous at all irrational numbers and discontinuous at all positive rational numbers. All right? So first of all, suppose you have x is irrational. Then you can get a sequence of rational numbers converging to x. Now, without loss of generality, I can assume the q sub n, the bottom part, is always a positive integer. If it isn't, I just multiply the top and the bottom by -1. All right? Now, I claim that if this happens, where x is irrational, that this q sub n must converge to infinity. So it must be unbounded. In fact, the limit of it has to be infinity. Now, if that were not the case, what does it mean? Well, it would mean that there would exist m and a subsequence such that q sub nk is less than m. Now, since I'm assuming they're all positive, it's not really necessary to take absolute values here. Okay, there are finitely many integers n that are bigger than 0 and less than or equal to m. Therefore, q sub nk is equal to one of these infinitely often for infinitely many k. So I can take a further subsequence such that q sub nk is equal to L, where L is somewhere between 1 and m. Well then, since this is a subsequence of a converging sequence, I know this also converges to x. Well, that's totally impossible unless these p sub nk's are eventually a constant. Because you see, whatever they are, they're integers. And if you're looking at integers of integer multiples of 1 over L, those cannot be getting arbitrarily close to each other, and so you cannot have such a thing converging to x. Remember, if a sequence does converge, then it must be a Cauchy sequence. Okay, so eventually this p sub nk must be a constant integer p, and therefore x is rational after all, which is a contradiction. Now, if you take x is irrational, then if you have xn converging to x, consider what happens. Well, f of x is 0. If x sub n is irrational, then by definition f of x sub n is 0, so it's real close to 0. If x sub n is rational, then eventually for large n, the denominator of x sub n will be very large, and therefore the value of this function will be very small, and so it will be close to f of x either way. So f is continuous at all irrational numbers. If x is a rational number not equal to 0, then it's not 0, and so I can look at a sequence of irrational numbers that converges to x. All right, and f of x sub n is 0, and that would converge to 0, but f of x is not 0. So you see, it fails to be continuous at every rational number, well, non-zero rational numbers, and it is continuous at every irrational number. What a strange function. Now, I believe it was Dirichlet that came up with this function, but I'm not sure. I have seen it called the Dirichlet function, and it is the sort of thing he would come up with, so it probably is due to him. All right, I would like to show that square root of x is continuous. Well, if I look at the square root of x minus the square root of y, this is 1 over the square root of x times this. So if epsilon is given, I could let delta be less than epsilon over epsilon times the square root of x. Now, the other case is that x is equal to 0, and in this case I'd let delta equal to epsilon squared, because you see, in that case I just want to say that the square root of x is small, provided that x is small enough. So I would just let x be smaller than epsilon squared, you see. And so this function is continuous at all non-negative values of x. Okay, all polynomials are continuous. Why is that? Well, because I know that f of x equal to x is continuous. In fact, if you're looking at the epsilon delta arguments, just let delta equal epsilon. And now, from the theorems in the chapter, I know that x raised to a power is continuous, and I know scalar multiples of x to a power is continuous, and I know sums of such things are continuous. In other words, I know that all polynomials are continuous. Now, what about rational functions? Well, rational functions are quotients of polynomials. So if you have a rational function, it's of the form p of x divided by g of x. Now, if you have x sub n converges to x, and it's in the domain of the rational function, so that g of x is not 0, then you know that this converges to that because of the theorems on convergence of sequences. Because you see, g of x sub n converges to g of x, and g of x is not 0, therefore this converges to that. So you see, rational functions are also continuous at every point of their domain. Now, if I look at this function, this is a strange function. 1 if x is an element of the rationals, 0 if x is not an element of the rationals, and I will let g of x be that strange, everywhere discontinuous function times this function. Determine where g is continuous. All right, g, if g of x is not 0, it won't be continuous, because whatever x is, you could get a sequence of irrational numbers that converges to x, and g of x sub n would always be 0, and that couldn't converge to something non-zero. Therefore, this function is not continuous at every rational number except for 0 and 1. Now, at 0 and 1, you see, this function g is equal to 0 because this expression is 0. Well, what about at these points? Oh, also, the function is 0 at all irrational numbers and also at 0, 1. Now, if you have an irrational number, all you have to do is take a sequence of rational numbers that converges to it, and the function will be 1 at those rational numbers. And so it will fail to be continuous there because g of x will not be 0 there. But I don't know yet about 0 and 1. See, these are the two interesting examples. Well, let's look at 1. If x minus 1 in absolute value is small enough, then g of x minus 0 is this, and that's smaller than this, and that's less than epsilon, because this is a polynomial, you see, and its value at 0 is 0. All right, so in fact, g of x is 0. Now it's similar for 0. So you see what happens is g is continuous at these 2 points, but it is not continuous everywhere else. See, not continuous at the irrationals. It's not continuous at any rational other than these 2. That's what we discussed. And it is continuous at these 2 points. So it's kind of an interesting example. See, up here earlier, we had one that was continuous at all the irrationals and discontinuous at all the rationals. Here we have one that is continuous at exactly 2 points and discontinuous everywhere else. All right, these are isolated points. Suppose you look at the integers. If you take any integer, it's further than 1 from all the other integers. Well, it's equal to 1. The closest integer to it is 1. Okay, so in the definition for continuity, I would just let delta be 1/4. And now, if you pick an x out of any of these integers, and you look at y closer to x than 1/4, then where's y? Well, it has to be exactly the same integer. And so f of x minus f of y will be 0, and that's smaller than any epsilon you cared to pick. So you see, it really doesn't matter what the value of your function is at these points. It will automatically be continuous. All right, now let's look at an example here. Give an example of a function f not continuous at some point, but absolute f is continuous. Okay, this function is discontinuous everywhere because you just approach whatever you are looking at by a sequence of points that are either rational or irrational. If the point you look at is rational, you pick irrational points to get it as a limit of irrational points. If it is irrational, you get it as a limit of rational points. Okay, so this one is not continuous anywhere, but absolute value of x is identically 1. Therefore, it's continuous everywhere. All right, find two functions which fail to be continuous, but whose product is continuous. Well, goodness, you could just let f and g both be this function here. Then f times g is identically 1. And that's certainly continuous. And yet both of these functions fail to be continuous anywhere. Find two functions which fail to be continuous whose sum is continuous. Well, let's use this function and let g of x be minus this function. Then their sum is 0, but neither function is continuous at any point. Find two functions which fail to be continuous, but whose quotient is continuous. Oh, I forgot to do that one, didn't I? Well, take this function and divide by itself, right? That would do the job, wouldn't it? And if you wanted two different functions, let g of x be this 1/2 on q and minus 1/2 on r minus q. And if you divide one by the other, what are you going to get? You're going to get 2, right? So the quotient is continuous, but neither function is continuous. Suppose that f is a function defined on R and f is continuous at 0. And suppose that f of x plus y is equal to this. Show that if this is so, then f of x needs to be x times f of 1 for all real x. In other words, the only solution to this here is f of x equal to a scalar multiple of x. Now this is a very famous functional equation. It's called the Cauchy functional equation. Very important example. Okay, first of all, let's note that f of x minus y plus f of y is f of x. So f of x minus y is f of x minus f of y. See, that's nice to keep in mind. Okay. Now, from the equation, if you have p and q are positive integers, if you look at q times p over q, that says f of this would be f of p over q plus f of p over q plus f of p over q, q times. So it would be q times f of p over q. And that's what this is saying here. All right. And so now this f of p over q is going to be, you see, this is just p over q here because this is f of p. See, in here, because the q's cancel, I could divide by q, and then I'd have 1 over q times f of p is f of p over q. That's where this is coming from. And now f of p, where p is an integer, is just p times f of 1. I mean, p is a positive integer, okay? Now, f of 0 is equal to f of quantity 0 plus 0. That's f of 0 plus f of 0. Subtract f of 0 from both sides, so f of 0 is 0. And so if you look at f of x, it's minus f of minus x. Why? Because if I add f of minus x to both sides, I get f of x plus f of minus x, which is f of x minus x. That's f of 0, and that's 0. Okay, so it follows that if I look at f of minus p over q, that's minus f of p over q. And that's minus p over q times f of 1. So what I've just shown is that in every case, without any exception, not even having to look at any assumptions of continuity, it follows that f of a rational number is the rational number times f of 1. So now, suppose you have a real number, and maybe it isn't rational, but you can let r sub n converge to x, where r sub n is rational. Then 0 is equal to the limit of this. Now, why would that be true? Well, this is where you're using the assumption that f is continuous at 0. This expression in here converges to 0, so the limit of this must equal f of 0, which, as we saw above, is equal to 0. So if I look at this, it's the limit n goes to infinity of f of r sub n minus f of x. And remember, we had that up there. So that says that f of x is the limit as n goes to infinity of this, which is the limit as n goes to infinity of r sub n times f of 1. Well, r sub n converges to x, so this is equal to that. And that tells me that this is the form that the function must have. Now, this is a very amazing result. It turns out there are other solutions. Of course, they cannot be continuous at the origin, at 0. And in fact, you can show that if you have any solution to this functional equation, which is not of this form, then the graph of this function must be dense in the plane, which is so perverted you cannot even imagine it. It would say that for any ordered pair in the plane, there is a point x f of x arbitrarily close to that point. There are a lot of really sick examples in math. And that is where we'll stop for now.